This is going to be a video on the Chapter 5 stuff for the stats final review. Or not Chapter 5, but the fifth review of the stats class here. This is going to be about z-scores, so stuff that was probably most recently done. So, when you're working with a normal distribution, which remember, a normal distribution is when you have a situation where most of your values occur at the average, and then you have a few values at the extreme. So this peak right here, that's the average. And then you have very small extreme values. So if you're talking about the heights of people, most people are around the average height, and you have a few very short people, and you have a few very tall people. So when you have this normal distribution, we can use z-score tables and values to help us figure out probabilities of getting people within a certain range if we choose at random, like for a sample or a survey, or if we just want to know the general breakdown of a population. Now, the thing you have to remember is that when you're doing a z-score table, that you always get probabilities from a z-score table that are to the left of the z-score. Just again, as a quick reminder, a z-score is simply a value on this graph here that represents a certain standardized situation. So, for instance, if I have if I draw my normal distribution, and I have a z-score right here of, let's say my z-score is um, 2, that means that whatever this value is, whatever this height is, it's 2 deviations above my average. So if my average height was 5 feet and my deviation was half a foot, then this z-score of 2 is 2 half feet above 5. So it's 2 deviations above 5. Now, again, my z-score table will get me the probability of picking somebody that is less than this. That's how my table works. It always goes from the left-hand value. If you want to get from the right-hand value, there's ways we can modify that. So it either gives it to the left of the z-score, or put another way, it gives you values that are less than the z-score value, right? So the probability of getting values that are less than 2 deviations from the average. Um, that's the reference point there. So first thing is, how do you even get a z-score? So the z-score formula is your value, x, minus your average, we'll call that x bar. Again, this is your average, AVG, divided by the standard deviation, right? We'll call that, actually, let's go ahead and do this as S, because usually we're going to be working with sample deviation. So we'll go ahead and put an S in there. So S, which again, this is standard deviation, and this right here, that is the value you're checking, or the value that you're working with. So value minus the average over standard deviation, which again, basically is just asking how many deviations above the average are you. That's essentially what this does here. So once you have a z-score, you can go to your table and look up the probability of getting that z-score or less. And again, the table will always give it to you in this way. It'll always give you less than the z-score value. So you look up your z-score value, you find the probability in the middle of the table, and you're good. I'll show you a table here. Actually, right now, let me show you a table right now. So this is our z-score table. So if I want the probability of getting a z-score that is 0.52 or less, well, here's 0.5, here's 0.02. So you find out where they cross, and you get 0.6985. So that's the probability of getting a z-score that is 0.52 or less. Not more, but less. So if I want the probability of getting one that's more than that z-score, what I do is I take that z-score and I subtract it from 1. Right? So it's the z-score, or it's not the z-score, the probability minus 1. So you subtract the probability value, called the p-value, from 1, not the z-score. So it'd be like 0.6985, and then that from 1. So 1 minus 0.6985. Not the z-score itself, but the probability you get in the middle tip. So these values in the middle subtracted from 1, not the z-score. And if you want between two values, what you do is you do almost the same thing you do for a greater than. You find the probability of both values, and then once again, you subtract. Oh, that's an ugly one there. Let me try that again. Myself right a little bit neater. So then whoa, I don't want the highlighter. Come on. So then you subtract the larger by the smaller. So you're going to have two probabilities. They're going to be two different values, and you simply subtract the bigger probability from the smaller probability, and that gives you the probability of getting between two z-scores. So let's put this into practice here just to kind of show you this in process, and maybe that might help some of you that are struggling. So IQ scores are normally distributed, so we can use this. Has an average of 100 and a standard deviation of 15. So I want the probability of getting less than 110. If I pick somebody at random, or if I want the general breakdown of the population, what percent of the population is less than 110 IQ? Okay, well, let's go ahead and do 110, my value, minus the average over the deviation. So that'd be 10 over 15. So let's just check that here in my calculator real quick. That would be 0.6 repeating. So we'll do 0.67 because these scores are rounded to the nearest second decimal spot or to the nearest hundredth. So 0.67 is my z-score. Let's go ahead and look that up in my table. So a 0.67 z-score gives me a probability. Here's 0.6, 0.60, 0.61, 2, 3, 4, 5, 6, 7. So 0.7486. That's the 0.07 mark. So this value right here, 0.7486, is my p-value. That's my probability. So that is my answer, 0.7486, or about 75%. So about 75% of the population has an IQ of less than 110. Let me just check that here to make sure I saw my table right. 0.7486. Right, yeah. So, decent chunk of the population has an IQ of less than 110. All right. What if I want bigger than 120? Okay, so once again, we need to find our z-score. 120 minus 100 over 15, which would be 20 over 15, which is 1.33, which is just twice this number. So 0.133, repeating, but I'll just do 0.133. So I want to figure out what's the p-value of this, 0.133. Let's go to my table here. Here's 0.1, 0.1, or 0.01, or sorry, 1.0, 1.01, 1.02, 1.03. Why am I looking there? A lot of you are probably screaming at me now because I made a mistake. That's 1.33, not 1.03. So 1.33 means we're right here. There we go. So 1.30, 1.31, 1.32, 1.33. There we go. So 0.9082 is that value. So that's my p-value, 0.9082. Let's go ahead and write that down. 0.9082. But that's the probability of getting somebody that's less than an IQ of 120. If I want more than 120, I'm going to take 1 minus that value because I want to be more than 120, not less than 120. So 1 minus 0.9082 would give me 0.0918. 0.0918. So that, about 9%, would be the probability of getting somebody with an IQ of bigger than 120 or more than 120. And if I want to be between two values, well, same thing. We're going to take our two values and we're going to find out their p-values and their z-scores, because we need to find the z-scores first before we find the p-values. So 95 minus 100 over 15. So let's figure out what these z-scores are here. So 5 over 15 for the first one, which was 0.3 repeating, 0.33. And then negative 5 over 15 for the next one, which is also negative 0.33. Right? So now we're going to find the probability value for both of these. So let's go ahead and look in our table here. 0.33. So here's 0.3. There would be 0.33. So 0.6293 it looks like. So 0.6293. That's 105 or less. Now let's get 95 or less. So that'd be negative 0.3 and then 0, 1, 2, 3. So it'd be 0.3707. Yeah, 0.3707. 0.3707. And then we just subtract these two values. So this value minus that value will give us the value of being between 95 and 105. So 0.6293 minus 0.3707, we get 0.2586. 86. So about 26% chance, or you could also say, instead of being a chance, you could say that 26% of the population has an IQ of between 95 and 105. So again, you can think about these as percent of a group rather than just probabilities of picking somebody at random, because they both kind of mean the same thing. The chance that you pick somebody at random is the same as the percentage of the group that is that category that you're looking for. So those are your three basic problems, right? Less than, greater than, and between. And they're all done very similarly with a little bit of a twist each time you do something other than less than. Now you can also have to go backwards. So going backwards means you have your probability or your percentage. Excuse me there. You have your probability or percentage, but you want to figure out what the z-score or the value is. Okay, we can do that. So let's say that the average amount of feathers on a turkey tiger is 80. The standard deviation is 4. We want to figure out, okay, what amount of feathers, what value, would represent the separation of the bottom 85% of the turkeys from the rest, or turkey tigers, I should say. Well, here's let's draw a diagram for this here, because again, that'll help clarify what we're doing. So I want the z-score, we'll put like right here. Here's my z-score. I want to know what z-score, not only what z-score, but what value represents the cutoff point here where 85% of the population is less than that z-score. Well, remember my z-score formula is z-score is equal to x minus the average over standard deviation. That's an S there, by the way, not a 5. Well, okay, I know my z-score, or sorry, I want to figure out my z-score, but I know that it's going to have to be 85% on the back end, right? Well, I can look that up, right? 85% is 0.85. I can look that up in my z-score table and kind of reverse engineer this. So if I go to my z-score table, I'm going to look for 0.85 in the middle here. So I'm going to look for what value has a p-value of 0.85. I'm going to try to get as close as I can here. So it's going to be up here somewhere, 0.85. So let's see here. Here's 0.843, 0.846, 0.848, 0.850. So it's going to be between these two values. So from these two values, which one's the closest to 0.85? Well, this is about what, 15 off, or 0.0015 off. This is 0.0008 off. So it looks like this value right here is a little bit closer if I'm doing my mental math right, which I believe I am. So this value is closer to 0.85, so we're going to go with that. So that's going to be a z-score of 1.4, or 0.04 in this case. So 1.04 is the z-score that at least closest represents 0.85. So my z-score here is 1.04. That's as best estimation as I can get. So again, I look this up in the middle, or try to get as close to this in the middle table that I can, and then I reverse engineer it to figure out what the z-score that goes with that is. So here's 1.04 as my z-score. But I want to know, that's not the amount of feathers. It's not like 1.04 feathers. That's just the z-score. I want to figure out how many feathers does that represent. So that's why I'm going to use this formula here. So I want to figure out, okay, what's the value, the x that goes with that z-score? I want to know the x that goes with that z-score. Well, I know that the average, which is what x bar is, the average is 80. I know that the deviation is 4. And like I said, I just figured out my z-score from the table. So this is an algebra equation I can solve. I can simply take 1.04, I would times it by 4 first, and then add in 80 afterwards, and you get 84.16 as your amount of feathers on a turkey tiger that represents the 85th percentile, or the amount of feathers that that represents more than 85% of the population. So once again, this backward problem just requires you to look up your p-value in the middle of the table first, and then go to the sides to figure out your z-score, and then plug it in your formula to solve. So what value would represent the amount of feathers that separates the top 20%? So this one here says the top 20%, not the bottom. So when I make my little graph here, there it is, I want the z-score. We'll do it right here. I need to figure out the z-score first that separates the top 20%. So right here, that's 20%. Well, here's the problem. My table only goes from the back end, remember. I can only look up values that are behind the z-score. So if that's the top 20%, that means this has to be the bottom 80%, right? Because 80 and 20 makes 100%. Well, that means that I'm going to look up 0.8 in my table. I don't want to look up 0.2. I want to look up 0.8 because I want the bottom 80% to be looked up to figure out the z-score that goes with that. Because my table is only going to give me from the bottom. It's not going to give me from the top. So you have to make that little mental conversion in your head there. So we're going to look as close to 0.8 as we can get, which looks to be about right here. So 0.7995 is as close to 0.8 as we can get. This is a little bit further over than this one, so we're going to go with this value right here. That's going to be 0.84. Let me just make sure I got that right. Yeah, 0.84. So this is going to be a z-score of 0.84, which then we do the same thing we did before. 0.84 is equal to my value minus the average, which is still 80, divided by the deviation, which is still 4. And then you just go back to Algebra 1 and you solve this problem using your basic algebra tricks. I won't necessarily write all that here to save you some time. This ends up being 83.36 is equal to the amount of feathers. So you need 83.36 feathers to separate the bottom 80% from the top 20% roughly, because again, we did use a little bit of an estimation to get this number here. Which again, kind of makes sense too, because if this separates the bottom 85% and this separates the bottom 80%, that means these two values are going to be fairly close because my deviation isn't that big. So these two values are fairly close, which is good because, again, they're fairly close in their representation as well. Bottom 85 versus bottom 80. There's not really that much of a difference. So that's a backwards problem. You go from the middle of the table to the sides, and then you plug it into your z-score formula, which is right here. There you go. Your z-score formula. You plug in those values and then solve it to figure out your x value. Again, this is the value that you're looking for. This represents the number of feathers, the x. This represents the z-score that's associated with it. And most of the times they want you to figure out the x, not just the z-score. Now, we can do that exact same question, but they might ask it differently. So they might ask it using something called percentiles. So percentiles represent situations where you did as good or better than X percent of the rest, where X is the percentile you're looking for. So for example, if I want the 35th percentile, that means I want the value. That's a little bit of a bad bell curve, but we'll go with it. I want the value that separates the bottom. I should have made my value much less on there. So let me try that again. That's going to be a bad graph there. Let me try that again. So I want the value that separates basically the bottom 35%. So here's my bell curve. I want the value over here, the z-score, that separates the bottom 35%, which is the exact same thing we just did, but it's just going to be said differently. So instead of saying the bottom 80%, they're going to say the 80th percentile. So percentile simply means what percent of the data is behind you. So 92nd percentile means that you have your bell curve here, as best as I can draw, and here's your z-score, and that means that you're better than 92% of the people that took the exam or reading or whatever. So this means that 92% is behind your value. So once again, just make sure you read the problems carefully, because again, it's no different than what we just did. It's just going to be said with different wording. Okay. So let's say the average heart rate for a sloth is 60 beats per minute. It has a deviation of 2.5. I want to figure out what value represents the 90th percentile. So once again, I need to think in my head here. Okay, 90th percentile. That means here's your z-score. 90th percentile means that 90% of the data is behind you. So you convert that to 0.9, and then you do the exact same thing we just did. You go to your table, where's 0.9? So here's 0.9, 0.90, or sorry, not on the side there. I did that completely backwards there. You want to look up 0.9 in the middle of the table. So you don't want to do what I just did. I almost did my z-score of 0.9. It's not a z-score of 0.9. We want to figure out a p-value of 0.9. So where is that? Let's see here. As close to 0.9 as we can get, which looks to be about right here. 0.8997. That's as close to 0.9 as we can get, I think. So that would be 1.28. So that is the z-score we want. So this is going to be 1.28. And then we set it up in our algebra, right? So value we want minus the average over 2.5. And then we do some basic algebra. Times 2.5, 60. And we get 63.2. 63.2 is equal to x. Which again, kind of makes sense because if my average is 60, and I want to be in the 90th percentile, that means I want to know what's the heart rate. What's the heart rate that's going to be above the average, obviously, right? If you're in the top 90%, or not top, but if you're above 90% of the data, that means you're going to be above the average, so your value should be above the average, which it is. If I want the 40th percentile, once again, without even doing the graph here, 40th percentile. Okay, so here's my z, and then behind my z is 0.4, right? So I want to look up 0.4 in my table, which if I go to my table real quick again, 0.4, not on the side, but in the middle here. So I'm going to go down to the negatives here. Anything below 0.5 is going to be the negatives. Anything above 0.5 is going to be the positives, just in case you didn't know that. So 0.4, let's see here, as close to 0.4 as we can get, which looks to be between these two values here. So 0.3974, that's what, 0.0026 off. This is 0.0013 off, so this is going to be the closer one. So negative 0.25. So here we go. That's going to be negative 0.25, if I read that correctly, which I need to go back and check that I did because I'm second guessing myself. Negative 0.25. Yeah, I got it. And so then we set that up in our equation. Negative 0.25 is equal to x minus 60 over 2.5. And once again, make sure you keep the negative in there because that's going to be crucial because that is a negative number. So negative 2.25 times 0.25, or 2.5 rather, and then add 60, which means we're going to get 59.38 is equal to x. Which again, makes sense because if we're only above 40%, that means 60% of the data is above us, right? So we're definitely below the average. Remember, the average is the one. If I draw my little bell curve again here, if you're at the average exactly, if you're exactly at the average, that means you're a 50-50 split. So 50% is below the average, 50% is above the average. So if you're at a 40-60 split where you're above the 40 but below the 60, that means you're below average, which is why you have a negative z-score. And if you have a negative z-score, that means your value should be less than your average, which it is. Not by much, because it's not really that big of a negative, but it is less. The more negative your z-score, the more below average you should be. And the higher your z-score, the more above the average you should be. The bigger positive you have, the more above the average you should be. So you can kind of use that to gauge whether you're doing your arithmetic right. All right, so the last thing we have here is usual and unusual. So usual and unusual is usually based on the number of standard deviations. So let's put SD here. Standard deviations it is from the mean. Now, again, we can do this one of two things. We can use it doing standard deviation, or we can even do it using probability. Let's go through the standard deviation one first. A value is unusual if it is more than 2 deviations from the mean. So if you're more than 2 deviations above the mean or below the mean, you're considered unusual. So if my average, let's say my average here, if my average was 10 and my standard deviation was 1.5, that means 10 plus 2 times 1.5 would be 13, and 10 minus 2 times 1.5, which would be what, 6. So 13 and 6 are my maximum, minimum, and usual values. So if I'm between 13 and 6, I am usual. If I'm bigger than 13 or less than 6, then I'm unusual because then I'm more than 2 deviations either above or below the average. A z-score, since a z-score represents the amount of deviations something is above or below the average, that means if your z-score is more than 2 or less than negative 2, you're unusual, because that's literally what it means. 2 means 2 deviations. Negative 2 means less than 2 deviations. So if you're less than negative 2, means you're lower than 2 deviations. If you're more than positive 2, means you're above 2 deviations. Therefore, you're unusual if you're within one of those two ranges. So if you get a z-score of 2.5, you're checking an unusual value. Now, in terms of probability, what this means, and this goes back to the empirical rule or the 68, 95, 99 rule. That was in a later chapter. If you want to look those up, you can. But basically, what it comes down to is that it has to be less than a 5% chance of occurring. If the probability of something is less than 5% chance of occurring, then it is unusual. Now, we've done a lot with z-scores this video, so I'm not necessarily going to go over getting usual and unusual from z-scores because we know how to look those up now. But let me expand on this one a little bit here. So, I'm going to actually skip the first one here. Actually, you know what? Let's do the first one because it's a pretty quick one. So, robots can produce a laser. Can fire a laser 200 feet with a deviation of 5 feet. What are the minimum and maximum usual values? So 200 feet is my average. I want to do 200 feet plus 2 deviations and 200 feet minus 2 deviations. So plus 2 deviations, again a deviation is 5 feet in this problem, would be 210, minus 2 deviations, again, 5 feet is a deviation, would be 190. So 210 is your maximum usual. 190 is your minimum usual. So if you're between 210 and 190, you are a usual range of firing. If you're outside those bounds, then you're unusual. Would flipping a coin 3 times in a row be unusual? Now, again, we're not going to look up a z-score for this, but we can do it with probability, right? The probability of getting tails 3 times in a row. Well, first time is a half, times second time's also a half, times third time's also a half. Whoops, a half. So a half times a half times a half is 1/8, and 1/8 as a probability, or as a decimal rather, is 0.125, which is about a 12.5% chance of happening, or exactly a 12.5% chance of happening, which would not be considered unusual. It's small, and it's probably not going to happen, but if it does happen, it's not unusual. And that's the thing about stats. There's a difference between likely to happen and unusual. Unlikely to happen, or not likely to happen, means that it's probably not going to happen, but if it does, we're not surprised. Unusual means it's probably not going to happen, and if it does, we are surprised because that really shouldn't have happened. And again, we're talking about happening in the course of many events over an extended period of time, right? Not just one instance here, but if something has a 5% chance of happening and you're tracking it over a period of time and it happens multiple times, well, in each setup, then you might have something that's worth investigating or correlating or something like that. So for example, if you uh, I just thought of a game here, but many of you probably don't know the game, and therefore the example is not going to make much sense. But if somebody drinks water and they live, right, the chance of you dying from drinking a glass of water is very, very low, right? We're definitely less than 5%, correct? Well, if someone drinks water and they die, well, we wouldn't necessarily consider that unusual, or we would consider that unusual, and therefore we want to investigate, okay, what's happening with that water that they drank? Was it tainted in some way? Was the glass they drank poisonous or whatever? If they drank a cup of water and died, your guess wouldn't be, oh, well, that's not likely to happen, but I'm not surprised. Your assumption would be, oh, that's not likely to happen, but I am surprised, and therefore we need to investigate why the heck that happened, because people don't die just from drinking glasses of water. So think of unusual as being unlikely to happen, and if it does, it's worthy of investigation in terms of why it did. Would picking a value above the 90th percentile be unusual? So here's, again, let's draw this picture here. So above the 90th percentile. So here's my value. I'll put my z-score here. Here's 0.9. Here's 0.1. So we want to pick one of these values. Well, let's look up in my table here of what the z-score would be. So 0.9, as close as I can get, right? So 0.9, 0.9, 0.9. I think the closest I can get would be right here. I think we did this once before. So my z-score for 0.9, which again, the best estimate I have is 0.9 or 0.8997, is 1.2 and 0.08. So 1.28. So that z-score is 1.28, which is not unusual. Right? Remember, a z-score has to be more than 2 in order to be unusual. This is not unusual. And again, it makes sense because what's the likelihood of you picking one of these values? Well, 10%, right? If 90% of the data is below your value, and you want to pick above the 90th percentile, which means you want to pick a value that's above the 90% of the population, well, whoops, my bad there. If you want to pick a value that's above 90% of the population, well, that means you have a 10% chance of doing so, because that means you're picking from the top 10%. But that's still not unusual. Again, people think being top 10% is good, and it is. It's a high value, but it's not necessarily unusual. It's not hitting that mark yet, because you have to be less than a 5% chance of happening in order to be unusual. So if you pick from the top, 3%, that would be unusual. If you want to pick from the top 3%, then you're trying to figure out people that are unusually high. So if you're in the top 3%, you're unusually high. If you're in the top 10%, well, it depends on how top of that 10% you are, but you're not really unusually high because you're in the top 10%, not in the top, 4 or 3 or 2. So again, if you need to convert into a z-score, do so, but all you're looking for is this value right here, okay? If you want to pick from these people right here, 10% of the population is not going to be unusual because you're still within 10%. All right, so that concludes this video here. Again, this stuff is probably the most recent in your heads here from the lessons that we've done. So hopefully it was a little bit easier going than most. If you have any questions, let me know. Otherwise, have a good day.